Heat transfer. It is everywhere. It is part of our daily lives, and the world is built around it. So whether we are cooking, the heat is transferred from the stove to the food. So to the place that we're living in, heat is transferred where warm air from the outside rises and the cooler air on the inside sinks. So that's why we are using air conditioning units to cool off the temperature of the room. And this system uses the principles of heat transfer to provide the cooling to indoor spaces. So the process of air conditioning involves the transfer of heat from the indoor air to the outdoor environment, which is achieved by circulating a refrigerant through the closed loop system. So there are also the things that we make, for example, like cars or like buses or aircraft vehicles in general, and spacecraft. So let's focus on the satellites. So satellites are exposed to extreme temperature variations in space. So ranging from the extremely high temperatures when facing to the sun and to the extreme low temperatures when facing in the shadow of the Earth. So in this video, we are going to tackle heat transfer and how it is applicable in aerospace systems. Heat transfer is the process by which thermal energy is exchanged between two or more objects or the systems that are at different temperatures. So heat can be transferred in three different ways. So we have conduction, convection, and radiation. Conduction. It is the transfer of heat between two objects that are in contact with each other. So heat transfer occurs due to the collision of particles in the material that is transferring the heat. So the temperature difference between the two objects causes heat to flow from the warmer object to the cooler object until they reach thermal equilibrium. The rate of heat conduction is dependent on several factors, including the temperature difference between the two objects, the distance between them, the material properties of the objects, and the cross-sectional area through which the heat is transferred. The thermal conductivity of the material is a measure of how well it conducts heat, and materials with a higher thermal conductivity transfers heat more rapidly. Convection is the transfer of heat through the movement of fluids such as air or water. It occurs when a fluid is heated and rises, carrying heat away from the source of the heat. So the convection can be natural or forced, depending on whether the movement of the fluid is due to the buoyancy forces of an external source such as fan or a pump. Radiation. It is the transfer of heat through electromagnetic waves such as visible light or infrared radiation. It does not require a medium and can occur in a vacuum, for example, space. All objects emit radiation in the form of electromagnetic waves, and the amount of radiation emitted depends on the temperature and properties of the object. So, in the aerospace industry, the aircrafts that we make, the satellites, the rockets, the missiles, the engines, they have certain electronic and mechanical components that are needed to be shielded from the harsh temperature conditions, whether it is in the air or in space. So these components must remain in certain temperature limits to achieve successful and longer operation. So this is achieved by the appropriate thermal design. So like the space shuttle, the bottom section, it is covered with heat shield plating to protect the outer structures of the spacecraft from burning while re-entering the atmosphere. And there are satellites with gold sheet coating to protect the critical components or instruments inside from the radiation of the sun. So let's take an example of how heat transfer is applicable in aerospace systems. I will be focusing on the conduction process of the heat transfer. We have this what we call thermal barrier coating or TBC. So they are usually found or applied to the metallic components that are exposed to high temperatures. So such as the turbine blades, the combustors, and the exhaust nozzles in gas turbines, diesel engines, and industrial furnaces. So these coatings are designed to provide a layer of insulation between the hot gases and the metal substrate, in which it helps to reduce the heat transfer and increase the component's operating temperature range. So here in this diagram, it shows a cross-section of the wall for a proposed combustor liner. So a combustor liner, it is found in the airliner's inlet of an engine, so right here. It has a titanium wall with a crystalline silica SiO2 ceramic thermal barrier coating. So due to the differential thermal expansion of the silica and titanium, a thin elastic polymer bond layer made up of a high temperature polymer material is placed between the two. So the purpose of this coating is critical to the performance and efficiency of gas turbine engines, as they must withstand extreme temperatures and pressures while maintaining the required level of combustion efficiency. We know that heat transfers from the hotter part to the cooler part. And if the temperature of the hot surface is greater than the colder one, so the temperature of the cold surface decreases to achieve thermal equilibrium. And in the context of mechanical properties, when a certain part exceeds its temperature exposure, the component will fail. So the different layers have a certain maximum temperature exposures that needs to be sustained and must not exceed its maximum to prevent the failure of the layer, and it depends on the thickness of each layer because it determines the amount of the maximum thermal exposure that the layer needs to maintain. And the amount of heat that is transferred are what we call heat flux. So here in the table, it shows that the thermal conductivity for some common materials. So notice that the titanium has a large amount of thickness while the crystalline silica ceramic has a small amount of thickness. So that is because materials or the metals such as the titanium is better at structural strength, but it cannot withstand at high temperatures. So as for the ceramic, it can sustain greater amounts of temperature, but it has a little structural strength. So that's why the ceramic is facing at the hotter surface while the titanium wall is next to the cooler area. So if the thickness of the layer is increased, so you can say that the maximum value of the hotter gas from the outer part of the area will also increase. That's why heat and mass transfer are critical considerations in aerospace systems because it affects the performance, reliability, and safety of such systems. So aerospace systems face several challenges related to the heat transfer. For example, at high temperatures, it can cause materials to degrade or fail, and the thermal stresses can be result from the differential expansion and contraction of different materials. So to manage these challenges, engineers uses a variety of techniques such as cooling systems, insulation, and heat shields. So today we learned about heat transfer, what are the forms of it, the aerospace system's application to heat and mass transfer, and its relevance in the field. So that's all for today's video. I hope we'll see each other next time. Goodbye, guys.
Approved for reset.